Hey guys, welcome to physics. To begin, you can click any of these tabs here on the right to take you to any portion of my lesson. This is just going to jump you to that slide in the PowerPoint so that you do not have to flip from slide to slide. So we'll begin with the introduction. These are your standards. We'll be doing some math and computational analysis. We'll be doing some of these skills to help prepare you for the math that is involved in physics. What information do you think you might need in order to solve this physics problem? A 59-kilogram physics teacher is walking on a slack line, a length of webbing stretched between two trees. At the point where her foot touches the line, the webbing applies a tension force in either direction. What is the tension in the line? There are some hints down here in the diagram. I recommend that you split your screen so that you play this video on the left and have your copy of these student notes on the right. That way you can fill in whatever you need and take notes as you follow along. So just go ahead and jot down some info here on what you think you might need in order to solve this problem. Pause this and come back when you're done. Okay, welcome back. So you may see here that you need an angle, and FG here would stand for force of gravity. So you might say, okay, I need the physics teacher's weight. You'll be able to, in this course, you'll be able to convert kilograms to pounds, pounds to kilograms to get a weight and then a force of gravity. And you may have come up with a few other ideas that you need. So what is physics? It's the branch of science that involves the study of the physical world, including energy, matter, and how they're related. So basically it is the study of matter and energy. And energy is what is used to cause motion. So we'll be studying how objects move. Objects are made of matter. So matter and energy. In physics, we express relationships in terms of equations, and we will use math to solve for the unknown. For example, in this course, you'll be given a word problem and you'll be asked to solve for the unknown. Here, the potential difference, symbol V or voltage, across a circuit equals the current, we use symbol I, multiplied by the resistance, symbol R, in the circuit. The formula that we would use is volts equals current times resistance. These in parentheses here are called units, which we'll be exploring today. So voltage is measured in volts, current is measured in amperes or amps, and resistance is measured in a unit called ohms. What is the resistance of a light bulb? So in solving a problem, you'll start by identifying what is the unknown. What is the resistance of a light bulb that has a 0.75 amp current when plugged into a 120 volt outlet? You'll also identify your knowns or given variables in order to solve the problem. So just a sample of calculations in physics before we learn these skills that you need to do these math problems. We will break down a problem into knowns and unknowns. Here we don't know resistance. We know the current is 0.75 amps, so we know that the voltage is 120 volts. You would simply use the formula, substitute in the values given. So for V, we have 120. For I, we have 0.75, and for R, we don't know. Now you use your basic algebra and divide both sides by 0.75 amps. $120 divided by 0.75 gives us 160 ohms. So this is just a sample of what you'll be doing in this course. Measurements and the metric system. Now, if you're doing this course at home, feel free to grab yourself a snack and enjoy. Take some notes. Again, split your screen so that you have the video on the left, your note taker PowerPoint on the right, and you can take notes on there. Also, have your science notebook open. I really encourage handwritten notes. That it helps with your muscle memory. If you've ever heard of muscle memory, like if you're a cheerleader, for example, you're out there, you're moving your arms to the music, and that is muscle memory. Eventually your body just does it naturally. So math or English or any subject is the same way. You want to write down information. You want to take good handwritten notes so that, when you get to the test or something, your hand is like, all right, I can do this. And it just starts to pour out in theory. But it's good to, learn how to write these math problems out. You're not just typing math on your computer. So, objectives for this lesson. You're going to understand why the SI units are important. Know the difference between a base unit and a prefix for the metric system. List 14 units of the metric system in sequence. Set up and use conversion factors in numerator-denominator format. Perform metric conversions using conversion factors. And convert to consistent units in order to add and subtract values. All right, type me an answer here on your note-taker PowerPoint. Which powers of the metric system can you name? And list them in order from largest to smallest. And go. Pause the video and come back when you're done. Pause it now. Welcome back. Let's take a look at the powers of the metric system. They're up here if you want to go ahead and compare your answers to what's listed. There are 14 that you're going to need to know. So, first, let's compare base units. There are 7 base units in the International System of Units. This is called SI. It's, I believe it's French for Le Système International des Unités. I do not speak French, by the way. Don't judge me. The base unit is the standard measuring stick for a physical quantity. For example, your quantities are length, mass, time, temperature, electric current, amount of a substance, and luminous intensity. The standard unit to measure length is not the mile and it's not the foot, it is the meter. You're going to abbreviate meter using the symbol M. For mass, we're going to use kilogram. We're not using gram, which is a base unit on the metric scale. We're using 1,000 times that. We're using a kilogram as the SI unit, the standard unit of measurement for mass. We abbreviate that kilogram. The reason these are important is because these are the units that you need in order to perform calculations in physics, unless otherwise noted. You learned about amount of a substance in chemistry, that is the mole, abbreviated MOL. Candela, sounds like candle, doesn't it? Well, that is a measurement of luminous intensity, or how bright an object is. These are the 7 SI units, the standard units of measurement. Meter, kilogram, second, Kelvin, ampere, mole, and candela. Units that you do not see listed, such as newtons for force, or liters for volume. These are derived units. That means they're a combination of the base units. For example, we use length for meter, but what about area? Why isn't that listed here? Well, area is derived by taking a meter of length times another meter of length. That is going to give you meters squared. Well, what about volume? Well, volume is meters times meters times meters. I'm going to draw another meter out here. I'm just going to stretch this image out. And what am I left with? Well, I'm left with a cube. Doesn't that look like a cube now? And that would give me meters cubed. So the SI unit is meter. Meters squared, meters cubed, or area and volume. These are derived units. So meters squared, meters cubed, derived units. Newtons is also a combination of multiple units. So understand the difference between a derived unit, which is not seen, and an SI unit, which is listed here. All right. We usually have a quick activity at this point where I have each group of students pick up an object to use as a unit of measurement. Now this could be hand, feet, whatever you and your lab partner want to choose. You want to use pencil as your unit of measurement, feel free. Now if you're doing this lesson at home alone, go ahead and pick an object around you, like a pencil or whatever you want. Now I'm going to have you guys find the length of a desk, or if you're at home, do the length of a room. We really want a standard though. So for example, in the classroom, we would measure the length of our desks, which ideally would all have the same length. And we would list our results on the board. So tell me, why do you think it's important to use a standard unit of measurement? What if one group is using hands and the other group is using feet, and we're listing, oh, I don't know, 12 and 13 and 11, and another person's using feet, and they're listing numbers such as 5, 4, 5.5, etc. Why do you think it's important to use a standard unit of measurement? Also think and tell me, how difficult was it to estimate a fraction of your unit when you got to the end of your measurement? Go ahead and answer these two in your PowerPoint notes. Okay, so after collaboration, you would find that if you just listed the length of a desk as 11 and somebody else listed it as 5, it would be really hard to compare those values. So if we all use a meter stick to measure the length of an object, we would all be getting very similar answers. Why are SI units important? So back in 1999, I was in, I think, like 9th grade. Anyway, a $125 million space probe called the Mars Climate Orbiter crashed on Mars. This was due to a very avoidable mistake. So the scientists used inconsistent units. What happened was one of the numbers was calculated in English units, like inches, while the other was set in metric units, like centimeters or meters. The conversions were not applied between the two systems, so the probe crashed and was destroyed. Now that is a huge waste of money, and I bet a lot of people were not very happy. What I'm going to have you do is click on this link and read the article and answer the 3 questions at the end. You're going to submit a screenshot of your answers on a Word document. I like to keep all my screenshots from you guys on a Word document because I use a tablet and that makes it easier for me to mark up your work and to send it back to you virtually. Okay, go ahead and do that and come on back when you're done. Pause it now. Welcome back. Let's take a look at a few examples of measurements. These are reference numbers. The Earth has a mass of 6 times 10 to the 24th kilogram. For comparison, a car is approximately 1,200 kilograms. Now time is all measured in seconds. Again, this allows us a basis of comparison because we're using the same unit for each of these measurements. Prefixes are used to modify base units. So although the SI units like meter and kilogram should always be used in calculations, sometimes other systems are used in measurements. If a measurement is given in English units, like pounds, you're going to need to convert that to kilograms before calculating. Sometimes prefixes are used, as in 23 centimeters. Centi here is the prefix. You'll need to convert to 0.23 meters before performing calculations because meters is the SI unit, the standard unit. A prefix is written before the base unit. So in this case, centi is the prefix and meter is the base unit. You can tell if an abbreviation is a base unit if there's only one letter. So I get this question a lot from my students. Well, is this milli? What is this? This is meter. So when it's by itself, it is a base unit. I'm not saying SI unit here, I'm saying base unit. So gram is a base unit. Kilogram is an SI unit, standard used around the world. So this is a base unit. S, seconds, a unit for time. All of these are base units, and there's only one letter. If there are 2 letters to the unit, the first letter is the prefix. C is for, that's correct, centi. M is for meter. So this is centimeter. G, the second letter is gram. The letter in front is, that's right, kilo, kilogram. Okay, is this meter second? What is this? I thought M was for meter. Well, again, identify the second letter first. This is seconds for time. M is for milli. So this is millisecond, the fraction of a second. So understand the difference between the base unit and the unit with a prefix in the front. Here are your prefixes. Listed here you have 14 prefixes. Now there are more, but these are the ones that you'll need to know for this course. In order to memorize these in the correct sequence, here's a mnemonic device for you. The great and mighty King Henry died by drinking chocolate milk made in Pensacola, Florida. V is for Tera, great, giga, M is for mega, kilo, hecto, deca, base unit, deci, centi, milli, micro, this one's tricky, nano, it's not the first letter, it's the second one, pico, and femto. Notice that the powers jump by 3 and then only by 1. So what we're doing here is we're going to start at the base unit and we're going to work our way up. 10 is deca, 100 is hecto, 1,000 is kilo, and then we're going to go up past 10,000, 100,000, go to million for mega. That's easy to remember. Mega, million. They both start with M. Then up 10 million, 100 million to billion, which is giga, and trillion for tera. On the other side of the scale, 1/10 of a base unit is a deci unit. So if we're talking about meters, this would be decimeter. 1/100th is a centimeter. 1/1000th is a milli. And then we're going to skip by 3, just like we did at the top. Micro, 10 to the negative 6th power. This is millionth. Then we go down to billionth, trillionth, and quadrillionth. You get the drill. Let's take a look at what these numbers mean. Take a little brain break. Click on this link. You have to allow Adobe Flash. And there's 3 levels of difficulty to choose from. What you're going to do is get a visual of how many small things fit in one larger thing. So how many small units fit in one larger unit. Play for like 5 minutes and then come back to this video. This is going to give you a better representation in your mind of, for example, how many nanometers actually fit in 1 meter, or how many milliseconds make up 1 second. So think about that as you play. Pause the video now. Come back when you're done. Pause it now. Welcome back. How'd you do? I'm going to walk you through a few class examples. These are on metric conversions. How many centimeters are in 1.85 meters? Now, in your science notebook, I want you to make clear notes. So I want you to label this section of your notebook, class examples, colon, metric conversions. And you're going to list these examples A, B, C, etc. Handwrite the math work, show the steps that I show you, and at the end, highlight your answers or circle them or put a box around your final answer to make it stand out. Okay, given this problem, how many centimeters are in 1.85 meters? I'm sure some of you can do this in your head, and that is great, but I'm going to show you how to do it on paper. 1.85 meters. You're going to set up a conversion factor. Conversion factors are 2 equivalent values. So for example, 1 hour is equal to how many minutes? 60 is correct. So if 1 hour is equal to 60 minutes, that is a conversion factor that can be used to convert from hours to minutes or minutes to hours. Both are equal. 1 hour is equal to 60 minutes. So here, I want to know how many centimeters are equal to 1 meter. Ask yourself, which one is smaller? Centimeter or meter? Let's take a look. Here's the metric system written out on a lateral scale. U is the base unit, so this would be meter here. Base unit, meters, seconds, grams, bytes. Centi, find centi. Centi is smaller than the base unit meter. So over here we have smaller units, units that are smaller than the base unit, and over here we have larger units. It means more of the base unit is needed to make up those. So we're going to go from base unit meter to centi. I'm going to go 1, 2. I'm counting 2 letters over. The metric system, I love this because it is based on powers of 10, and that means that 10 to the second power centimeters, or 100 centimeters, are equal to 1 meter. That is my conversion factor. 100 centimeters all lined up is the same length as 1 meter. Now you might see this written as a different way, a fraction of a meter, or 10 to the negative 2 power of a meter, or 0.01, that's 10 to the negative 2 power of a meter, is equal to 1 centimeter. I tend to use these conversion factors and not these, but either one is correct. Now that we know that there are 100 centimeters in a meter, I'm going to go back to my slide and write my conversion factor. 1.85 meters times, we're going to do this in fraction form with centimeter and not centimeter. We're going to do this in fraction form using a numerator and denominator. I need to know what goes in the denominator. That's in the bottom. Centimeter or meter? Which one? Okay, it's going to be the one that you start with. So I'm starting with meter. That means the meter goes in the denominator. I know that 1 meter is equivalent to 100, or 10 to the second power, centimeters. That is my conversion factor. Now this is like saying I have 1.85 meters over 1, that's a fraction, times 10 to the second centimeters over 1, and that's going to equal 1.85 times 10 to the second, or 185 centimeters. So just like in math, if you have x divided by x, in this case m divided by m, they cancel out. Whatever you are left with, in this case, becomes your new unit. So 185 centimeters. You do not have to write the parentheses or the 1 with your starting factor. You do have to write parentheses, numerator, denominator to show me what conversion factor you are using. Okay, 185 centimeters make up how many meters? Write down what's given. This is your starting factor. We need a conversion factor. We have centimeters, meters. Which one is smaller? That's correct. Centimeters is smaller, so we will have more of them. How many more? Well, as we determined before, 100 centimeters make up 1 meter. Now, because I'm starting with centimeters, I'm going to put that on the bottom this time. And I will put 1 meter on the top. These are equivalent values. This is a conversion factor. Crunch those numbers. 185 divided by 100, or 10 to the second, equals how much? This is the same as saying, okay, if I divide by 100, I'm going to move my decimal point, my invisible decimal point, 2 places to the left. 1.85 meters. All right, so again, this is like saying over 1. So if I were to look at this as 2 fractions, 185 divided by 1 times 1 over 100 equals 1.85 meters. But you do not have to show the parentheses or the 1 with the starting factor. Okay, let's go from smaller unit to bigger unit. Convert 341,000 microseconds to seconds. How many microseconds make up a second? Find micro. Micro is smaller than the base unit seconds. I'm going to count 1, 2, 3, 4, 5, 6. So 10 to the 6th, or 1 million microseconds, are equivalent to 1 second. So 10 to the 6th. What goes in the denominator, seconds or microseconds? That's correct, microseconds, because that is the unit we're starting with, and we want to put it numerator to denominator so that they cancel out. We know that 10 to the 6th, or a million microseconds, make up 1 second. Okay, go ahead and take 341,000 divided by 10 to the 6th. What do you get? I want you to pause this video, put those numbers in the calculator, and then we'll check your work. All right, pause it now. Welcome back. So remember that dividing by 10 to the 6th is like taking this decimal and moving it 1, 2, 3, 4, 5, 6 places to the left. So you should get 0.341 seconds. All right, for the last one, convert 0.0051 megabytes to kilobytes. Let's go and see how many powers there are between kilo and mega. Here's kilo. Kilo stands for 1,000. And here's mega. Mega stands for million. 1, 2, 3 powers of 10. So 10 to the 3rd kilo make up a mega. Remember, kilo is smaller. So the 10 to the 3rd goes with kilo, not with mega. All right, so megabytes cancels with megabytes when we put 1 megabyte in the denominator. 10 to the 3rd kilobytes goes in the numerator. So our conversion factor here is 10 to the 3rd kilobytes per megabyte. Now we multiply 0.0051 times 10 to the 3rd, then we get 5.1 kilobytes. It's always a good idea to check your work. Does this answer make sense? If we're converting from 0.0051 megabytes to kilobytes, and megabytes are bigger and kilo is smaller, we should have more kilobytes. So our answer should be bigger than what we started with. And it is. 5 is definitely bigger than 0.0051. Example E, a roll of copper wire contains 15 meters of wire. What is the length of the wire in centimeters? Write down your starting factor, 15 meters. Write down your conversion factor. 1 meter is equivalent to 100, or 10 to the 2nd, centimeters. 15 times 100 gives you 1,500. What's my unit? Centimeters. And you may have done that in your head, and that is just fine, but I do need you to show me your work on paper so that I know that what you're doing in your head is correct. Show me those conversion factors. It does get more difficult, so using the metric system and bouncing left and right on this metric scale is easy now, but when we start dimensional analysis, you'll be working with different types of units and it won't work like that. So moving the decimal is great, but you need to learn the skill using this conversion factor. You can use conversions in this simple math, adding and subtracting. When you do this, you have to make sure that all units are the same. So for example, can you add 1 hour and 30 minutes? You can't do that simply. You have to convert to the same unit. Yeah, you can say 1.5 hours, but for consistency here, convert 30 minutes to hours. So 30 minutes times 1 hour is equivalent to 60 minutes. So 30 divided by 60 gives me half an hour. Now I can add 1 plus 0.5 and get 1.5 hours, so 1.5 hours. I know in like normal conversation you would say 1 hour 30 minutes, and that's fine, but we're learning some skills here. So convert your units to the same unit whenever you add or subtract. When you multiply and divide, you do not have to have the same units because they will multiply and divide just like variables in math class would. For example, if you had x times x, then you get what? You get x squared, right? And you can do that. If you had x times y, well, you get xy. It's the same thing. So here, 4 meters divided by 2 seconds will give you 2 meters per second for your units, meters per second. If 2 units express the same measurement, they must be converted to common units. So these are the same units here, time, convert them to common units. Now, here we have 2 different units, but they both express the same measurement of length, centimeters and meters. You cannot multiply 3 times 0.1 because 3 centimeters times 0.1 meters is incorrect. Convert one of them. So here we're going to convert from meters to centimeters. So their 1 meter is equivalent to 100 or 10 to the second centimeters. So we get 10 centimeters. Now you can do 3 times 10 gives you 30 centimeters squared. So remember that your units are going to multiply just like variables in math. X times x gives you x squared. Centimeters times centimeters gives you centimeters squared. All right, I hope you enjoyed those skills using the metric system and basic mathematics. Let's take a little brain break and click on this link here. You're going to do a quick metric system fill-in. You can screenshot that and add that to your Word document for your submission.